Welcome everyone. Today we'll be talking about different configurations for backup power using the MNPower inverter and batteries. Backup power is a main desire for using this equipment when doing grid-tied systems, and there's some considerations in designing these systems for the best performance. First, when we're doing backup power, we need to think about the difference between power and energy. This is very important when we're doing our design and understanding the suitability of this equipment for different purposes. Power is watts, and it is the instantaneous rate of electricity use, measured in either watts or kilowatts, and often we'll talk about amps, which is amps times volts equals watts. This is analogous to speed or miles per hour. How fast are we going? How fast are we using electricity? It's just a snapshot of an instant. It doesn't really tell us much about what's happening over time. That's where energy comes in. Energy is measured in watt hours or kilowatt hours, and it's the cumulative electricity use over time. Watts times the hours that those watts are being used equals watt hours. This is analogous to the distance we travel over time, the miles as opposed to the miles per hour. It's a cumulative value, and we can either make up that distance, that cumulative energy use, with high power for a short amount of time, or it can be low power for a long amount of time, or if we had high power for a long amount of time, it's even a larger cumulative kilowatt hours total energy use. Sometimes you'll see people use watts per hour. This isn't a real unit of measure. It's like saying miles per hour. So that's not an actual unit of measurement. Either we're looking at watts to measure power or watt hours to measure energy. So as we go through, we need to think about those two different values, energy and power, when we're looking at different components and doing our design. The power and energy ratings of the MNPower equipment. The all-in-one inverter is 10 kilowatts continuous output power. That's 42 amps at 240 volts AC from battery power. During the daytime, when the sun's up, it can actually do higher power, 47.5 amps or 11.4 kilowatts. So if you have loads that you know are only going to be used during the daytime, during sunny days, you can use this higher value. But if you're looking at backup power at night or times where it might not be sunny, the 42 amps or 10 kilowatts is the value you want to use for the continuous output power. The PF16 batteries, the PowerFlow 16 batteries, they are 8 kilowatts continuous power output, so you need 2 of them to get the full power output of an all-in-one inverter. If you just have one of them, it's going to limit your power output of the inverter a little bit. PowerFlow 5 batteries are 3.7 kilowatts continuous, so you need 3 of them for each all-in-one inverter to get the full output power of that inverter. Now, most of the time when we're looking at batteries, we're looking at the energy storage, the total cumulative electricity they can store, not how fast we can get it out. For that, we're looking at 16 kilowatt hours for the PowerFlow 16s and 5 kilowatt hours for the PowerFlow 5s. Usually we only want to use 80 to 90% of that. We don't want to go all the way to 100% because then we get into issues of sudden shutdowns when we get to that last little bit. Just like you want to refuel your car before it gets below empty, give a little reserve so you don't run out in the middle of the road. So that's why we use 80 to 90% of the storage rather than 100%. When we're doing a system design, we want to start with a spreadsheet of all the different loads, how many watts each load is, and how many hours per day it's going to be operating. That'll let us calculate the watt hours each day that it's going to use. There's a lot of kind of general estimates and stuff that people try to use instead of doing the full spreadsheet, but the proper way to do it is the full spreadsheet, all the loads that you want to back up, and an estimate of how many hours per day each one's going to operate. Some loads, like refrigerators, it can be more accurate to use like a kilowatt meter and see how much energy per day they use, because they're kind of not coupled well together, the power use and the energy use. So anything that's kind of turning itself on and off automatically, like refrigerators, doing an actual measurement and getting the energy use that way can be more accurate than trying to estimate hours per day that it operates. What we're trying to figure out is our total continuous watts of load that we're trying to serve, and the energy storage required, and also the surge wattage. That also comes into play in sizing our inverter. With large motors especially, they can take anywhere from 3 to 10 times the running watts when starting the motor. Older well pumps, fridges, freezers, other compressors, air conditioners are typically the heaviest surge loads. Some of the new well pumps and any inverter driven or ECM compressors, which is a lot of the new heat pumps, have no starting surge, but older well pumps and kind of more traditional air conditioners have very heavy starting surge, so we need to take that into account when sizing the inverter. When figuring out the energy storage, we can calculate from our spreadsheet how many watt hours per day of energy that we need, but then we also need to think, how many hours or days of backup power are we going for? Are we trying to survive a 4-hour power outage or a 4-day? Typically, this one, the energy storage, is where you're going to get into territory that your typical design of a house electrical system really doesn't give you much guidance. Typical electrical load calcs when sizing the panels on houses are all about power. What's our peak power coming through? Do we have enough amperage? Do we need a bigger load panel to handle that peak power for the house? They're not really concerned about how long is that occurring. Does that peak power occur for 30 minutes or 22 hours a day? That's a massive difference in the energy use, with no difference in the sizing of the equipment as far as amperage of the main electrical panel. So it's when we get into energy storage, that's kind of a new calculation that won't be in your traditional house design. Like I said before, we want to plan on discharging the batteries to 10% state of charge. We don't want to go all the way down to 0%. So we're going to take our rated energy storage of the batteries and multiply that by 0.9 for the usable storage. And when we get into longer outages, say the 4 days, week-long outages, usually we take into account that there's going to be some recharging of the batteries from the sun each day. We're not operating purely from batteries once the grid goes away. This is where we get into the designs more like an off-grid system, where we're thinking about how much sun are we getting, how about in the typical months where we're designing for backup power. If we have winter storms, maybe we don't assume very much sun for recharging. If it's in a time of the year where we typically do have a lot of sun, when we might have grid outages, maybe we can assume that we're having good solar input and good recharging from the sun each day. Depends on the particular situation. And with the setup of our inverter, we can also use a generator for additional backup power. We'll talk about that a bit later as some of the benefits of that versus just using a generator. Here's the typical how we would wire in one of our all-in-one inverters to provide backup power. We've got 200 amp panel served by the grid. Here's our normal loads. Those are our non-backed up loads. And then we have 100 amp feed going to the AC input of our all-in-one inverter. And then the AC output is 100 amp feed going to the backed up loads panel. There's 100 amp pass-through and 100 amp transfer relay in the all-in-one inverter. And when the grid is up, it can send 100 amps through to that backed up loads panel. When the grid goes down, that transfer relay opens, and we have now only 42 amps of backup power going to that backed up loads panel. That's how much maximum power we can supply to backed up loads when the grid is not there. How much time we have for that depends on how much we're really loading it and how much storage we have. So that's kind of our basic, simplest setup for backup power. Now, in addition to this, that I always recommend is having a service bypass. This is so we can send grid power straight to the backed up load panel in case something goes wrong with the inverter or we're servicing the inverter system, that we don't lose power to those backed up loads when the grid is available. The all-in-one inverter can pass power through even when it's off, when it's in standby with the current firmware. But if it has a fault, and that includes array faults, it does not pass power through. In older systems where the array was on separate charge controllers going to the batteries, and the inverter only drew power out of the batteries to the loads, an array fault would not shut the inverter down because they were separate pieces of equipment. The all-in-one, it's more compact and more convenient having the array inputs built into the inverter, but it does introduce that issue that an array fault can also shut the inverter down. And a lot of the faults we encounter in systems do tend to be array faults of some sort, especially as arrays get older, and if you haven't put squirrel guard on the wiring and chewed wires. Just lots of issues you see as the arrays age. So, good reason to have a service bypass so that if something does go wrong, you can still get power to your backed up loads past that inverter instead of relying on it to pass them through all the time, if for nothing else, while you're working on it to get it restarted. Now, a lot of people don't include this, and what I've seen a number of times over the years is 5 or 10 years after the system's installed, maybe 15 years, long time's gone by, and something happens and it shuts down, and they just call the closest electrician they can find on a weekend to come bypass it and get power back up to the backed up loads. Electrician comes and they connect a jumper from the grid breaker panel over to the input of the backed up loads panel. Okay, it's got power again. But what I've seen a number of times is they forgot to disconnect the feed from that backed up loads panel to the inverter, and now there's grid power to the backed up loads panel, and it's feeding back into the output of the inverter, and that can blow the inverter up. So a temporary bypass by someone not familiar with the system can actually destroy the inverter in some cases. So that's why having a bypass wired in as part of the system is a good idea and one that I strongly recommend. There's a couple options for how to do this. On the left side here, we have basically a interlock switch where we can have 2 breakers feeding this panel. a main breaker and then a backfed breaker here. And one of those is the output of the inverter feeding the panel, and the other is a grid feed feeding that panel. So we can select which of those feeds that backed up loads panel. This is often the cheapest to implement, just the cost of this little adapter plate here, which is 20 to 50 bucks usually, and another breaker here with a feed feeding into it from the grid. Sometimes, if you're required to have an external disconnect for the backup power to the house, it can make sense to just make that external disconnect a 2-pole disconnect, like this manual transfer switch here, where one direction is sending grid power to the backed up loads panel, one direction is sending inverter power to the backed up loads panel, and then you have a center off to serve as your service disconnect. So it's not just a service bypass, it's also your service disconnect for code reasons if you're required to have an external service disconnect for your backup power. Another way to do it is to use an auto transfer switch that we would typically use with a generator, only we wire it a little differently. We need the type of auto transfer switch that can operate without a generator. The Kohler RDT series is one that I've been using. But in this case, we would wire it so the inverter goes to the primary input of the transfer switch and the grid to the secondary, kind of reversed of how you would normally wire it with grid to the primary. So it always uses the inverter output as your main feed to the backed up loads, unless for some reason the inverter output goes off, and then it automatically just feeds grid power through to the backed up loads. So 3 different options for doing that service bypass to make sure that even if the inverter is off or down for some reason, that you still have grid power able to feed to those backed up loads. What about backing up the entire 200 amp service? This is something that more and more we're asked about. If the house is already wired, it might be difficult to separate out the backed up loads. Maybe it's in a separate part of the house, not on the exterior, not in the garage where we have access to our service. And it'd be a lot of drywall work to rewire it. Sometimes it's just that the customer doesn't want to pick certain loads for backup. They just want everything to be backed up. Our internal pass-through and transfer relay is only rated for 100 amps, so we can't use that when we're feeding a whole 200 amp service. Some all-in-ones do have a 200 amp pass-through capacity, and that seems like that might be a better design, but there's really some serious drawbacks to backing up the entire 200 amp service, and we're going to go through a couple cases here on how you can do it and what a lot of the typical issues are and why we don't do it. Why we recommend not backing up a 200 amp service with a single inverter. Although you'll see a way right here that it can be done. So if you want to use a single Midnight Power all-in-one inverter to back up a 200 amp service, we'll use an external automatic transfer switch, 200 amp rated, to essentially connect it in. Here's the drawing of that. So we've got our 200 amp auto transfer switch, and then go into our main breaker panel, which is our main grid breaker panel, but it becomes our backed up panel as well. And the output of the inverter goes into the secondary of that transfer switch, same place where we would feed in a generator input. So if the grid fails, it just switches over to using the inverter output to power all the loads. Now here's the tricky part. We need to feed the AC in, the grid input of that inverter, upstream of that transfer switch. If we take our AC in off of our main grid breaker panel here, when that transfer switch switches over, it's going to see its own power coming in the secondary, going into the main grid breaker panel, back into the inverter, we get a loop, and the inverter just becomes confused because it says, oh, the grid is up, but the grid is myself. That doesn't work, and it's just going to shut down. So that grid feed of the inverter has to be from above on the grid side of that 200 amp transfer switch. So that can have some complications depending on the exact service. Like I said, the Kohler RDT switches are one that can operate without a generator. There's a lot of transfer switches out there that have to be paired with a specific generator, and those are not going to work when being used with an inverter system like ours. But there are some that are essentially independent and can be used with any two power sources to switch between them. In this case, we're running the grid into the primary and the inverter into the secondary, just like you normally would with the transfer switch. One drawback of this is that there's a several second delay in switching over between grid power and secondary power. When we're using the internal transfer relay of the inverter, there is essentially no transfer time, and you won't even notice when it switches. This, you're going to see the lights go out for a second or two, and then it's going to switch, and they'll come back on when the inverter takes over power. But that's really not the most serious drawback. Here's the more serious one. What if there's more than 42 amps of loads on that panel when it switches? That's a 200 amp panel. There could be a lot of loads on there, especially in a lot of these all-electric houses nowadays. So the grid fails, the transfer switch switches, and the inverter sees whatever that load is when it switches. If that's 80 amps, it's just going to say, blech, and shut down. Sometimes it's only a little bit over. I've seen one that it was pulling about 50 to 52 amps, and the inverter would handle it for about 30 seconds to a minute, and then it would shut down. And it took a little while to figure out, oh, we're just overloading the inverter just by a little bit. So we need a real careful assessment of the loads on that panel. Is that load really expected to remain below 42 amps, even though it's a 200 amp panel, if we're going to be backing it up with a single inverter? A second issue is, even if we stay below 10 kilowatts, 42 amps, that's still a lot of energy use. If we're pulling 10 kilowatts and we have two PowerFlow 16 batteries, that's 3 hours of backup power. Not very long. And that is another big issue with backing up the entire load panel, is we often have a lot of loads on there that aren't actually that important to back up, but they just happen to be on there drawing power, and because we're backing up everything, we've got to calculate in the energy use for all those extra loads that really aren't that important, because they're on that panel and they're going to draw power when it switches over, and that's going to drain the energy out of the batteries. A lot of customers will explain that they're just going to manually shut off loads to keep them under the power limit or not waste energy if they're off grid, and they don't need to separate out just backed up loads. They'll just control their loads. This is almost never a good idea, and there's a couple reasons for this. One is, if we're backing up the entire house, first of all, they may not even realize when the grid goes down because the whole house is backed up. So they don't even know to go shut off less important loads or shut off some of these heavier loads that could overload the inverter. Second issue is that they don't even have time to shut off the loads, because that automatic transfer switch takes 2 or 3 seconds after the power outage on the grid before it just switches all the loads to the inverter. unless they're standing right next to the load panel with their hand ready to just flip off those heavy load breakers, it's too late to prevent that overload on the inverter if you've got an 80 amp grid load and you got 2 or 3 seconds to kick off a bunch of big loads before it dumps that onto the inverter. That's if the owners are even home during the outage. What if they're in town and by the time they get home, non-important loads have drained the batteries and they don't have any for the next 2 days that they would have if they only had the important loads on there. Biggest issue that we run into really is just that customers don't actually think they use that much electricity, and they don't have a good concept of how much power different things take. So they say, I'm barely using any power. Well, barely any power, say it's 1 kilowatt. That's 24 kilowatt hours a day. That's 1.5 batteries drained in a day. Get into a 4 or 5 day outage, that's quite a bit. So maybe barely any power is still too much for a reasonable sized battery bank. And also what I've run into a lot is that the concept that power use of appliances is somehow related to the physical size of the appliance. And where this specifically seems to occur is space heaters. Like, oh, it's just a very small space heater. Can't possibly draw anywhere near as much power as the TV, even though it's drawing 8 or 10 times as much power as even a fairly good big screen TV in a tiny plug-in space heater. The amount of power they require is more to do with what it's doing, and anything creating heat is drawing a lot more power than virtually anything else in the house. So not having a good idea of what's drawing power keeps people from really making effective decisions when they're turning things on and off, trying to preserve battery energy. Now, our inverter has several smart load outputs. Could we use those? Partially. They're good for doing energy control, but not power control. So, because the smart loads are triggered based on battery state of charge, it's fairly easy to say, well, maybe we want to run an air conditioner on nice sunny days, even if the grid is out, because we got plenty of solar. That's pretty easy to program the smart load, so if the battery state of charge is above, say, 90%, it'll run the air conditioner, but once it drops below 90%, it shuts it off, so we don't drain those batteries running the air conditioner when the sun's not there. Or I've seen ones where we do an EV charger with the same sort of control. Turn it on when the batteries are full and we have extra sun, but don't let it pull the batteries down. But the smart loads can't control based on power. So if we've got too many amps of loads connected to that inverter, the smart loads aren't really helping with that. Maybe in the future we'll have a way to program them based on total power and control that as well. But right now, they're really energy controls where we control how much we pull out of the batteries, but they're not solving the issue of overload of the inverter. We can have contactors or smart breakers, which can be controlled to just dump some of those heavy loads in if the grid goes down. But if we're just going to automatically dump some of those heavy loads when the grid goes down, why don't we just connect them straight to the grid and not try to connect them to a panel served by the inverter at all? And depending on which ones they are and what kind of control scheme we have, we always run into the issue of, can we be triggering those from the inverter, or does it have its own control? There's a lot of different smart load panels out there, but really integrating them with the inverters is still very on the cutting edge and involves a lot of time figuring out communications and interfacing between them at this point. So I don't consider that a really good solution yet. Ideal would be is if we could stage loads and say, okay, I've got several heavy loads on here, but only turn one on at a time. Like, for example, we could say we've got an EV charger and a large air conditioner, and if the sun's out, I can easily run one or the other of those and the rest of the house, but I can't run both of those at the same time. So you could say, well, if the EV charger isn't drawing any power, turn on my air conditioner, but when I plug something into the EV charger, then drop the air conditioner to prevent overload of the inverter. That would be ideal, and right now that's all in custom independent control stuff, not built into either the inverters or most of the smart load panels that I've looked at so far. Another option when we're doing a 200 amp service to prevent overload of the inverters is use 2 or more of the all-in-ones. 2 inverters gives us 84 amps continuous and a full 200 amp pass-through, so we can back up a 200 amp service without an external transfer switch, and we get 84 amps continuous, which is still nowhere near a full 200 amp service, which is actually rated at 160 amps continuous, but it's a lot closer than 42 amps. There's a lot fewer 200 amp services regularly running more than 84 amps than there are ones that regularly exceed 42 amps. And we could always go to 3 inverters or even 4 if we really wanted to fully back up that 200 amp service no matter how heavily it's loaded. Of course, we also need to think about energy. We need a sufficient battery bank, getting larger and larger as we get more inverters put together here. Here's a diagram of how that works, showing 2 inverters. We have our grid, which used to feed this main grid breaker panel here, and instead we now run it into a grid input panel. This is usually what I do is a 200 amp 8-space feed-through panel. So we take the feed-through lugs and run that to our service bypass, and then 200 amp breakers in there going to the AC input of each of our 2 inverters. Then the output of the 2 inverters feed together into an inverter combiner panel, which then feeds our service bypass, and we can select either our inverter input for it or the grid input for it and send that to our what used to be our main grid breaker panel, which is now our backed up loads panel. And in this way, we've backed up our entire 200 amp loads panel, and we have full 200 amp feed through capacity through the inverters, quick switching so we don't have that power blip when we switch over to inverter power from grid, and we've got a lot higher capacity, 20 kilowatts or 84 amps in this case. And we could just keep on adding more inverters here with the same equipment on the sides, add more breakers up to 4 in this 8-space feed-through panel and feed 4 inverters and really have full 200 amp. Another place where I see this a lot is where we've got a 400 amp service to the house that splits into 2 200 amp feeds, and we decide we want to back up one of those 200 amp feeds as the backed up loads panel, and we just put 2, 3, or 4 inverters on that one loads panel to fully back up that and have the other one be non-backed up loads. Looking at energy storage, how many batteries do we need? Really depends on how long of a power outage and how much power we're using, how much energy we need. Up to 20 of the PowerFlow 16s or 20 PowerFlow 5s can be stacked. So if using the PowerFlow 5s, that's 100 kilowatt hours. If using the PowerFlow 16s, that's 320 kilowatt hours. But only 5 PowerFlow 16s, 80 kilowatt hours total, are allowed in a residential garage per code. So once you get higher than that, you're looking at separate power buildings to have your batteries and inverters in, rather than having them just in the garage. Utility rooms are typically limited to 40 kilowatt hours, or 2.5 of the PowerFlow 16s. Obviously you can't do half a battery, so 2 of the PowerFlow 16s, or 8 of the PowerFlow 5s in a utility room, or 5 of the PowerFlow 16s in a garage. So you can see that the system has a lot more capacity than what we can typically do in most residential code, where we need separate power buildings and things, which larger systems often have these. But if we're doing backup power for a typical house, we need to think, how much can 80 kilowatt hours really do? If we're just running lights, power for controlling a propane or natural gas fired heating system, and say internet, fridge, miscellaneous stuff like that, it can do quite a lot. If we start trying to back up heat pumps or any sort of heating appliances, electric heating appliances, 80 kilowatt hours doesn't go very far. Some houses with electric heat can easily be 100 to 200 kilowatt hours a day. So you can see 80 kilowatt hours doesn't get you very far there. This is an issue with all electric houses, which are becoming more popular. Even when we're looking at efficient heat pumps, it's still a much higher electricity demand than a natural gas or propane heated house. So it becomes a lot less able to do backup power for that house with reasonable size of battery banks. And as we discussed, houses that we don't select just selected loads, but just back up everything, we tend to have a lot more of the phantom loads that drain batteries a lot faster than we anticipated. So even if we don't have electric heating loads on there, just random phantom loads of stuff that wasn't that important but just happens to be on there will tend to drain the batteries more. One thing we can do, if we don't have enough battery storage capacity to get through the length of outage we're looking at, and we're looking at times of the year for potential outages when we don't expect much solar input to help out recharging each day, we can add a generator to the system. The all-in-one needs a pretty large generator, ideally 15 kilowatts or larger, and this is getting us into the range of permanent pad-mounted generators, usually propane or natural gas fired, and obviously these larger ones are going to be 240 volt output. Smaller generators can be used as long as they're 240 volt output, but you're going to have much slower charging time. And with the size battery banks that we're looking at, if you're charging at 4 or 5 kilowatts out of a small generator, that can take a long time to recharge, say, a 40 or 60 kilowatt hour battery bank. So we're really looking at larger generators as something that gets paired with our inverter systems, not the portable gasoline-powered generators you drag out of the garage. The question comes, well, if I'm going to have a large pad-mounted generator, what's the benefit of that, of having all these batteries and solar versus just the generator for backup power? And it depends on the situation. In some situations, maybe just the generator is better and a straight grid tie solar system that doesn't interface with it at all. But a lot of cases, we may have say we've got 10 kilowatts of peak loads on backup, but most of the time it's only 1 kilowatt of load. A generator is not very efficient when it's running at 10% of its rated power. So it can actually be a lot lower fuel usage, not to mention maintenance time on the generator, to run that generator for 2 or 3 hours a day at high load to recharge batteries and then run off the batteries in the inverter for the other 24 hours a day, rather than having that generator run for 24 hours a day, occasionally running a high load, but mostly running a much smaller load. If you have a high constant load, a generator running direct into that load might be more efficient. If you've got, say, a large heat pump drawing 5 or 6 kilowatts, maybe pairing that directly with the generator just to run that heat pump could be more efficient than recharging batteries, running them down, recharging them, running them down. But most residential loads tend to be what we call very peaky. They have high peaks, but the average isn't all that high. And in that case, an inverter with batteries is a lot more efficient at running that and then recharging from the generator for short periods. What if we don't have an interconnection agreement with the utility? In all of this discussion so far, we've assumed that we have an interconnection agreement with the utility, and the solar system is essentially operating in parallel with the grid. If we don't want to go through the paperwork of getting the utility interconnection agreement, which in some cases it's just paperwork, with some utilities it can actually be very difficult. But if we don't have that paperwork in place, we can't operate in parallel with the utility. If they find out that we're operating in parallel without the appropriate approvals, they do not like that at all, and they may actually just shut off your utility connection, remove your meter. The new smart meters can detect if there's solar operating in parallel often, because as loads go up and down in the house, say a really large load suddenly turns off, the solar may inadvertently export power to the grid, even if it's only for a second or two, for 100 watts or less. The new smart meters can see that, and so they're going to notice that a lot more than they did in the past. With the old mechanical meters, a second or two of low-level export as the loads changed wasn't going to show up. Now it's a lot more likely they're going to notice that and say, "What are you doing? You don't have approval for that. You need to remove that solar immediately." So what can we do? What we have to do is we don't operate in parallel with the utility. Instead, we have essentially the loads are served either by the utility or the solar, but they're never operating in parallel. This is kind of more similar to how we would do a standard backup generator. So here's one way of wiring it. We have our transfer switch, and instead of a fuel-powered generator going into the secondary, we have our output of our inverter going in there. And then if we want to charge the batteries from the grid, we have a 60 amp feed going into the generator input of the inverter. So the generator input of the inverter is treated differently than the AC in grid input of the inverter. It doesn't operate in parallel with this. It just uses it as a charging input. At that point, the inverter is nothing more than a big battery charger operating from the grid. It's not operating in parallel with the grid as an independent power source. So there's no chance of us accidentally selling back to the grid in this scenario. In this exact wiring here, there's also really no benefit of having solar on here other than the ability to recharge during a power outage, because In normal operation, we've got grid power. This transfer switch is sending that grid power through to the breaker panel. The inverter has no load on its output. It's just going to a set of contacts in here that isn't connected. So there's nothing for it to do. So if we add solar on there, all it does is keep the batteries topped off, but it doesn't have any benefit other than that. Now here's a way we can set it up so we do get some benefit of having the solar, but still don't risk backfeeding power into the grid. Here we've got our main grid breaker panel connected to the grid, and we're pulling off 60 amps going into the generator input of the all-in-one inverter. So same as before, it's just acting like a big battery charger on that input. It's never selling back. It's not operating in parallel with the grid. But we do have a backed up loads panel, which is normally connected to the output of that inverter. So if we have solar on that inverter, it can be operating our backed up loads from the solar and the batteries most of the time, unless the batteries get too low, in which case it switches over, starts using the AC generator input as a battery charger, and recharges the batteries that way. So there we get some benefit from the solar, but we still avoid operating in parallel with the grid. So that wraps up the presentation on different configurations for backup power using our inverter. If you've got any questions, email me at zeke@midnightpower.com.